Yesterday we learned the remainder theorem, which said if you plug in whatever value makes the factor 0, so if you plug in a into the polynomial, the answer you get is your remainder. And a branch of the remainder theorem is something called the factor theorem. It says if your remainder happens to be 0, if there is no remainder, that means that that is an actual factor. And it's leading to what we're going to be trying to do today. All of what we've been doing so far has been leading us to be able to factor things we haven't factored before. So we start off with example 2. And example 2 says, which of these are factors? So you have two options. If something's a factor, we know that the remainder has to be 0. So to find out if the remainder is 0, we can either use the remainder theorem or use synthetic division. We saw yesterday that often synthetic division is better because it's easier mental math. Of these 4, I would probably only use the remainder theorem for the first one. In fact, the first one, super easy to plug in -1 and do the mental math. And when I plug in -1 and do the mental math, it is equal to 0. Which means that x plus 1 is a factor. But I'm also going to show that you could have done this with synthetic division. So had you done synthetic division, right, we do our setup. I notice that they're in order. Nothing's missing, so I don't have to add any zeros. And you would also get a remainder of 0 from synthetic division. Another thing I'd like you to do on this question is put this in brackets and we'll write let p of x equal that. So I'm going to get you to write the division statement. And in writing the division statement, that's another benefit of the synthetic division. The synthetic division sets you up that not only do you find out that it's a factor, but I can write the division statement from the synthetic division. Right? Dairy Queen plus the remainder, and since the remainder is 0, you don't have to write anything there. Now, before we go to B, what I'd like you to do is leave some space before we start B. Because I'm going to do something later with this. So write your division statement. Not a lot of space, maybe a line or 2. We're just going to write one more thing underneath. Before we get to B, in B, we're now dividing by x minus 3. Since that's a bigger number, I would use synthetic division right away. And again, when you use synthetic division right away, our remainder is 0. And this tells us that x minus 3 is a factor. And just like we did in A, I'll get you to write the division statement and leave some space. And I'm going to get you to try part C on your own. So I want you to set up the synthetic division and find out if it's a factor on your own. All right, let's see how you did. Did you get a remainder of 0? And so that too is a factor. Kind of funny, I think that the textbook made 3 in a row that were factors, but they did. So you can check your numbers if it didn't work out, see if you made a mental math mistake. And then I'll get you to do leave space again. And then I'll get you to do part D as well. All right, let's see how you did on part D. So on part D, it does not work out. You get a remainder of negative 168. So that makes it not a factor. When we write the division statement, now there's this extra number at the end, so it hasn't factored out perfectly. Now, one thing that we found in this example, okay, is that we found 3 factors. An x cubed equation, I'm going to just zoom out here so we can see everything. It's going to be a little bit small. An x cubed equation will have up to 3 factors. An x squared equation only has up to 2. An x to the 4 could have up to 4. And we found 3 of them. We found x plus 1 is a factor, x minus 3 is a factor, and x minus 4 is a factor. In fact, we can go right beside this now and write this out. It's going to be equal to x plus 1 times x minus 3 times x minus 4. And that would be considered factored completely. And that's going to be our final goal of this section, is to be able to factor something completely. So then the question is going to be, is this what we have to do? Do we have to keep on guessing and checking until we find all 3 of them? And the answer to that is no, because that could take a long time. I mean, in this question, they gave us ones to check, and it happened to be that 3 of them worked. But our job is going to be, how do we find the ones that work? I'm going to look, and we're going to analyze this a little bit. Well, first of all, here we go, zoom. The question was, do we have to find all 3? The answer is no. If you find 1, look what happens. So here, for example, in A, we found 1. We found x plus 1 is a factor. We wrote the division statement, and if you would, and this is what I'll get you to do in the space that was extra underneath, you can factor this because this is a quadratic. You know how to factor that. It's going to be x and x. 2 numbers that give you 12, 4, and 3. They would both be negative, and you factored it completely. And notice you found the other 2 factors. Right? Because we found out that x plus 1, x minus 4, and x minus 3 were the 3 factors. If we factored this completely, we would have found all 3 of them. The question is, does it matter which one you find first? The answer is no. Look at the second one. If you found the x minus 3 first, and then you factor this quadratic, you'd have x and minus 4 and plus 1. You'd get the same factors, just in a different order. And same thing with the last one. So if we can find 1, then we can factor the other ones, and we could factor it completely. So then the next question becomes, how do you find the first one? Are you just randomly guessing? No. Okay? For example, we're going to go back to the top here. If this was the question with the p of x, and they said, find 1 factor, and one of you said, well, I'm going to try x plus 5. I would look at you and say, terrible choice. I can tell you right away x plus 5 is not going to work. And they're like, well, how do I know if something's possible? Another student says, I'm going to try x plus 6. Now, we know that x plus 6 doesn't work, but if we didn't know that and someone said, I'm going to try that, I'd say, maybe. That's not a bad choice. Much better than the x plus 5. X plus 5 is a terrible choice, but x plus 6 is okay. How do we know which ones are possible and which ones right away are impossible? And it has to do with how things work when you multiply. I want you to notice that when this is factored completely, there's a 12 here. Notice the numbers 1, -3, and -4, when they're multiplied together, make 12. Your last term will always multiply out to be the last numbers in each of your factors. Can you see why 5 was a bad choice? 5 doesn't multiply nicely to get 12. 6 was an okay choice, because it could have been like a 6, a 1, and a 2. And so this is something called the factor property, which is at the bottom of the page. Factor property says you look at the last number. This last number here in this example is a 10. That means that the factors that are possible would have to be either 1, 2, 5, or 10. 3 would be a bad choice. It would never work out nicely. So when we're looking to factor something, we're always looking to factor something with nice numbers. And that last number, the constant term, is going to be the one that helps us figure that out. So now we're going to go to our last example.